Welcome back this afternoon. I'm chairing this session where we're going to have some talks on the projects that were funded under what was called the Large Mathematics Call last summer. And we have 4 talks, and we'll start with Mark Brewer. Mark, over to you.
Hello there. I don't seem to be able to share my video. There we are. It's back. Well, hello everyone. Like I say, I'm a stand-in today really for Marcel van Ooyen, who is the leader of this project, but unfortunately couldn't make this this week. He's otherwise engaged, so I'm afraid you've got me for a bit. So this is our project, Drought Risk Analysis for Forested Landscapes, otherwise known as PRAFOR. Oops, it's gone on too. Okay, so PRAFOR is the nickname of this, and our project partners, as I've said, it's been led by Marcel at UK CEH, and with colleague David Cameron also at CEH. Then we've got myself, I'm the Director of Biomathematics and Statistics Scotland. Then as partners on this project, we have colleagues from Forest Research, James and Georgios. We have Mikko from Natural Resources Institute, Finland. And we have Miguel Zavala from the University of Alcalá in Spain. In brief, the aims of the project are to firstly build on some earlier work that Marcel has done in risk analysis with earlier models in this kind of context, and then to develop that risk analysis and apply it to examples from data sets in forestry environments in the UK, Spain, and Finland, and this choice of this set of locations, I think, is a good one because it looks at 3 very different parts of Europe. So we have some very good testing environments there, and some good data sets as well. And the third and final aim would be to, of course, develop a decision support system, and the basis for that will be an existing decision support system, which was created by Forest Research. That decision support system is known as ESC-DSS, and the aim of this system is to help forest managers and planners, etc., to select the tree species which would be specific to a particular location. And it's simplistic in operation. It's very easy to use. You just need to input location details and a soil type at the basic level. You can provide apparently more information. You can provide information on soil quality and things like that, and then you'd get a more precise answer. But at its basic level, it's straightforward to use, and that can be obtained. It is available for download on the Forest Research website. Another origin of the work in this project relates to the model BioSS, because we will be looking at models in this project. And related to BioSS, this is where Marcel was starting to do some work on risk analysis. So this is where that came from. Now, BioSS was a project led by what was then just CEH, and it was led by David and Marcel, both on this project. It's a basic forest model. Even though it's a basic model, it seems that it's quite complex to me just by looking at these things, because there were 17 variables, 17 state variables, that is, 9 relating to trees and 8 relating to soil. And then there were a further 19 output variables, including things like greenhouse gases, that's into the system and out of the system, both trees and soil, and things like productivity as well. And that's also available for download on the website of the International Soil Modelling Consortium. Another model which is going to be involved in this project, excuse me, is 3PGN, but I don't know much about that. I won't say much about that. But again, that seems to me a much less simple model. That's a more complex model. Okay, so probabilistic risk analysis, in a nutshell. I mean, this is a very, if you like, a simplified view of risk analysis. And the work that Marcel started with BioSS was looking at the relationship between what we might think of as environmental variables, X, and system variables, Z, where the environmental variables could be things like climatic variables, they could be drought indices, rainfall, etc. And system variables could be things like productivity or income relating to a stand or something like that in a forestry context. I mean, the interesting thing that I think we've noticed following on from some of the discussions that we've had on things like coupling of models and joining models together is that in some models, what might be seen as an environmental variable, something like soil quality, that could actually be a system variable in another model. So what the classification is between an X and a Z could depend on the context. And one thing we do want to take care about is that responses, the nature of this relationship could be changing over time, and that's actually highly likely when it comes to things like, when we consider things like climate change. Now, as I say, BAS4 took a simplified view of risk. It didn't deal with exposure at the first instance, and furthermore, it took the X domain. And I think for reasons of illustration, I'm going to be thinking of a single X variable and a single Z variable. So we've got a single environment and a single system variable. So if we could take that single environment variable and split it into two regions according to a threshold, then we can think of one side being corresponding to a hazardous situation and one being a non-hazardous situation. And in this context of this project, where we're thinking about drought risk of supply to forests, and we might look at, for example, either drought index or rainfall or something like that. So if the rainfall X is below a certain level, then we might consider we have a hazard, which is a drought condition. And that would be denoted by H, and we have not H, which would mean that we're not in a hazardous situation. We think of the standard definition of risk as being expectation of loss, which then is just the expected value of the system, given that the hazard hasn't occurred, subtracting the estimate, the expected value of the system, given everything that we don't know, whether the hazard is there or not. This is a thresholded view of the X domain. We're saying that where everything, the risk is related to a particular hazard, a particular threshold defines what that hazard is. And because of that, we end up with a discrete definition of the probability of the hazard occurring or not. And that does simplify things. And that means that we can then explore the relationship between vulnerability and risk and thresholds quite straightforwardly. So it's useful as an indication. Whether we stick with this in the future is to be determined, but that's what we're doing at the moment. Of course, the other definition of risk would be to relate the hazard with vulnerability, or ecosystem vulnerability in this case. And that means that you write the risk as being the probability of the hazard multiplied by the vulnerability. And those two definitions of risk themselves mean that we end up with a particular implicit definition of what vulnerability must be. Because if you simply rearrange the last equation and then put the expectation of loss definition of risk into the equation as well, you end up defining vulnerability to be the difference in the expectations of the system between non-hazardous and hazardous regions. So that's a specific definition of vulnerability, and given the previous definitions, that's the only definition of vulnerability that applies, in mathematical terms at least. What this does mean, this simple definition, is that we can then explore the relationships between R and V and thresholds and so on. And in this very simpler exploration here, we're going to look at a single X, a single environment variable, and a single system variable. And we're going to assume, for the sake of argument, that they follow a bivariate unit normal distribution with a correlation of a half. And in terms of our threshold, we're going to assume that perhaps X is rainfall, and therefore low X is bad if we're looking at the risk of drought. Of course, you'd have a high X was bad if you were looking at risk of flooding, but we're looking at the risk of drought in this situation. The first plot on the left, I mean, this is imagining that, so this is, for example, the probability of a hazard. So that's the probability that X is below this threshold. That's how we're defining the hazard here. And of course, if the threshold value is very high, then the probability of the hazard is almost 1, given that this is, as we've assumed, a normal distribution with a standard deviation of 1. So if the threshold value is set to 2, then the hazard is almost guaranteed to occur. That's the hazard, not the risk, of course. Now, on the right hand, what we have is a plot of the conditional probability distributions of the outcome variable z, given specific values of the threshold. So the 3 curves that you see correspond to 3 specific values of this threshold, defining the hazard categories on the environmental variable. And if the threshold is set very high, that's the value of 2, that's this blue curve here, if you can see that, then the conditional distribution of z, given x being less than the threshold, is almost the same as the distribution of z in the first place. It's almost the original normal distribution, because, as we've said, the hazard is almost certainly likely to occur. But as we can see, because the z's and the x's are correlated in this system, and that could just, I mean, this is a very simple system, but you would imagine in more complex systems that these things would be related. You would imagine that the productivity of a stand would be highly dependent on the rainfall, for example. So that's a very realistic situation. We can see here that as the threshold changes, the conditional distribution on z is also changing. So that's the productivity, the expected distribution, if you like, is changing. And we can go further than that. We can go further because we can also compute the expectations of this outcome variable z, the system variable z, for a general threshold. It's not just the specific thresholds here, but we can do it for any threshold. And that's what we're showing here. On the left hand, what we have are these expectations of the previous curves that we saw on the right hand side of the plot, previous slide. Now this black line, that's corresponding to expectations of our outcome measure. Expectations if the hazard is attained. So that's what these values, this black line here. So that's if the hazard has occurred, this is the expected value of our outcome measure, and that corresponds to the line, one of the curves on the previous slide. Well, actually, sorry, it corresponds to the expected values of all of these curves for those specific threshold points, but you can, like I say, you can compute it for general values of the threshold. And the red curve here, the one at the top, that's the expected value of the outcome if the hazard is not attained. And that is directly then the complement of the curve at the bottom, the black. These then, you'll notice these 2 conditional definitions of the expected value of z here, depending on whether the hazard is or is not obtained. The difference of those 2 things is the definition of vulnerability that we obtained. So literally the vertical difference here in the direction of threshold here is the value of vulnerability that we calculate. And you can see that they get narrower in the middle. So we plotted that here on the right hand side, this black curve at the top, that's the calculation of vulnerability. And we can see that the least vulnerability occurs in the center. And that doesn't surprise us in this situation, because the stability that we have in the center of this normal distribution effectively that we have is what's providing this lower vulnerability in the center, because as soon as you go out into the tails, that's where the skewness kicks in. In terms of the risk, that's also plotted here in the red, and that in this case it's the same. Because the expected value of the z is just 0 all the way here, it's literally just the same. I mean, in general terms, they would be proportionate, but in this case, they are exactly the same because of the simple definition of the z being a normal distribution, having normal distribution. Okay, so that's all about the project risk, the probabilistic risk assessment. The aims of the project, as I've said, is to extend the theory that we have so far to include things like exposure, and also to have a better handle on uncertainties. Now, for these simple kind of models that we've looked at to begin with, you can work out, you can derive exact formulae for the estimators for these cases and for these quantities. But for more general terms, of course, we are planning to implement all of this in terms of a proper Bayesian modeling framework. And then we'll go on to apply these, as I've said already, into particular data sets. And the next step is then to take these forest models that we've seen and to apply them to the data sets that we have, and to go back to our forestry colleagues and say, well, using these models, can we identify what are the important drivers of vulnerability? What set of situations might cause high vulnerability? And then from that, we want to go on to suggest actions that might be taken to reduce all of these quantities, either the probability of the hazard occurring, to reduce exposure, or even to reduce the vulnerability directly itself. And we have to acknowledge here that these particular actions, maybe they will have different costs, and they will have different impacts in each of the 3 countries. So that's something that we can study. And the final step in all of this would be to then embed all of this in a Bayesian decision theory framework, and to develop a decision support tool on the basis of that. But doing all of this in the Bayesian way ought to mean that we have a good handle on modeling uncertainties in particular with all of this. We've been playing around, these are early days of course with this project, we've been playing around with different models on different schematics for thinking about how we could think about Bayesian decision theory in this context. And the empty circles that you see here, the ones that are not shaded, this part of the model is relating to the model of our environment and our system. And in this particular schematic here, we have the Z, which is the benefit that we accrue from this system. So that could be the income that we obtain from the forest stand, whereas Y could be something that's a more direct model output. That could be the productivity relating to some X, some environmental and inputs. And in the rest of this graph that you see, we have the parameters theta, we have some epsilon, we have some uncertainty. And then related to that, of course, ultimately at the top, we have utility. Now, one note I'll say to Peter Challoner there is that despite 2020, we're all optimists, so we're dealing in utilities rather than loss. We might, by the end of the year, decide to change that. The utility is the thing that we're trying to maximize or optimize in some way. And there will be costs associated with the actions that we choose. And we've had discussions about what this graph should look like. At the moment, we've got action pointing towards productivity. So that could be an action that you take which may directly impact productivity. But of course, there are other actions you could take if you're thinking about Brexit, if you're thinking about trade tariffs. There could be actions that you take that would affect the income rather than the productivity. So you might need to have a line going from this action box A to Z, the benefit directly. And that might even depend on what sort of actions you're talking about. So there are different ways we can think about this graph here, which is embodying what we're thinking of. Okay, so that's me. Just very quickly, we do have our own page, of course, on the Landscapes Decisions website, and there's a picture of some trees. Thank you very much.
Thank you, Mark. Are there any questions? Can't see any on Slido if I'm working it properly. So I'll ask my own. I'll abuse my privilege. This hard threshold. So something is okay on this side of the threshold, and I up it by 0.1, and it's not okay. That seems to me to be rather artificial.
It is completely artificial, and that's why we've been really looking hard about uncertainty in that threshold, because you either say, well, I'm just going to deal with a continuous function, if you like, or we say, well, actually there is a threshold, but we're going to allow that threshold to be unknown, or at least uncertain. So you can consider a range of scenarios. But you're absolutely right that picking one threshold and saying that's true, it would be wrong.
So part of your Bayesian extension is actually making that threshold have some distribution.
That would be the aim of it. I mean, and you imagine within the framework that ought to be possible.
Yes, no, I can see possibly how to do that, and that might be easier than having a continuous threshold thing, yes. Whatever it's called.
Yeah, the might is what we're studying at the moment.
Yeah. Okay. Are there any more questions? No, if some turn up, we'll come back to you at the end. So thanks very much, Mark.